Good morning, everyone. Today we're looking at Unit 7, Lesson 5, Investigating Properties of Circle. So we're going to look at some more properties of a circle and talk about what those things mean in terms of the circle, and then we have to pull on some of that previous trig knowledge to help us identify certain things within a circle. So first, chords. Remember, we talked about chords yesterday. So chords are straight lines that are formed by touching 2 points on the circumference of the circle. So for example here, we could have a chord A, B, and we could have a chord C, D. All right, so I'm just going to draw those chords. All right, and we're going to say that this middle here is O, like the origin. So this first point is saying that chord AB is going to be equal to CD. And the reason that that is true is because the distance from the origin is the same. So that length there would be the same. So AB is equal to CD. We could kind of look at that on the other side, and if we had chords like this, right, the chords aren't what is important here. It's just pulling on both points here. And if we were to draw from the origin to that chord and say that this is S and say that this is T, right? Well, we just said that that distance is the same. So now we've created these chords OS, and that's going to be equal to chord OT because that's the distance from the center to the chord, and we know that's going to be equal in measure as well, right? So something to be familiar with in terms of a right bisector. So a right bisector is a line from the center of a circle that is perpendicular to a chord. It bisects the chord. So again, if I had a chord here, and we'll call this chord AB, and we were to draw a line from the origin, and it was a perpendicular bisector. So this perpendicular means it's going to form a right angle, and we'll call this point D. Okay, well, if it bisects it, it means that on either side of that point of intersection, they're going to be equal in length. So that means that from A to D is going to equal from D to B. Okay, so a couple ways to look at that rule is that we could say that a line from the center of a circle to the midpoint of a chord is perpendicular to the chord, right? So that perpendicular bisector, or that line OD, is perpendicular to that line AB. You could also look at it and say the right bisector of a chord passes through the center of a circle. So if we look at it from kind of the end, from the perimeter of the circle or circumference, in that right bisector ends up crossing the center of the circle. So all things to think about in terms of right bisectors. Okay, the next one, tangency. So a tangent line, remember, is a line that touches the circle just one time. Right, only once. We talked about that. Secant touches it twice, but the line of tangency only touches the circle once. So it says the line that is perpendicular to the end point of the radius of a circle is tangent to the circle. So if I was to draw the radius to that tangent line, it forms a right angle. Or we could say it's perpendicular to the tangent. All right, and our center is at O again. Okay, some other things to investigate in terms of tangents. If you have two tangents on a circle that are on the outside of the circle, these tangents will be equal in length in terms of where they hit the circle. So if I put some point out here, let's call it point C, and we drew straight lines from those points, where they hit the circle are going to be equal in length. So if that tangent line hits at point A, and this tangent line, let's try that again, this tangent line hits at point B, right? Those two tangent lines are going to be equal in length. That's what those hash marks mean. So we could say that line CA would be equal in length to line CB. Okay, a few more things to investigate in terms of the property of a circle. So twice the angle. So this comes back to the idea of the central angle and the inscribed angle. So if I have a central angle here, remember the central angle is formed by two radius, all right? And say they're touching the circle at AB, right? And then I make an inscribed angle from those same points. Okay, and we'll call this point up here C. All right, it says that if a central angle and an inscribed angle are subtended, which means they're extended by the same chord, so the chord being AB in this case, right? Our chord is AB, and subtended just means extended from, right? So the angle is created. The angle is created by extending two lines on either side of that chord to make an angle. And they're on the same side of the chord. The central angle is going to be twice the inscribed angle. So this central angle, if our inscribed angle is theta, then our central angle is going to be 2 times theta. So what I mean by that is that angle AOB is going to be equal to 2 times angle ACB, right? So my theta, or ACB, is going to be half that of AOB, or AOB is going to be 2 times whatever ACB is. All right? So the central angle is twice whatever the inscribed angle is. Okay, let's keep moving along. So chords and central angles. Equal chords subtend equal central angles and equal inscribed angles. So what I mean by that is if we have equal chords, we go back to that first point where we said chords that are the same length or the same distance from the middle of that triangle. So if we have A, B, and C, D as a chord, right? And these are chords that are equal in length. Well, if we were to subtend them to that center, right? Make some kind of central angle here off of each of those chords, then the angles that they make at the center are going to be the same. So we know that AB is equal to CD, CD, and because of that, angle AOB, which is that central angle we made, is going to be equal to angle COD. All right, so that's true of a central angle, but it's also true of an inscribed angle. Let's just put it in a different color. So if we have two chords and we create an inscribed angle from that chord, so if I have chord AB again, and I make an inscribed angle, remember an inscribed angle touches the perimeter or the circumference of the circle, and we'll call that, let's call that E, right? Then this angle here, this theta here, is going to be equal to that if we do that with a chord that's of equal length. So again, A, B, and C, D are of equal measure. So the inscribed angle that we make by extending from each sides of those, call that F, is going to be the same. So again, AB, that chord, is going to equal CD. And then because of that, those inscribed angles are going to be equal to each other. So that inscribed angle we could represent as angle AEB, and that's going to equal angle CFD. Those inscribed angles will be the same. All right, so a few more to look at. So chords and inscribed angles. So if two angles are inscribed on the same chord, the angles are equal. So this one's a little different. So this is looking at just one chord. So if we have one chord, and we'll call it AB again, and we create two different inscribed angles from it. So say we create one inscribed angle over here, like we really extend that end of the B part of the chord to the left side of the circle, and we'll say that it's touching at point C. Then this angle in here, angle C, is going to be equal to that if we subtend it the other way, like we extend from the A all the way over here and then B here, right? We're extending from the same chord just in a different direction in the circle. So those inscribed angles we create from there would also be equal. So we could say angle ACB is going to be equal to angle BDA. All right, one more, and then go kind of try some of the practice problems that relate to these property ideas. Okay, so it says right angles. Oh, that should say angles, not angels. I think it's correct on your notes. An inscribed angle subtended by the diameter is a right angle. So an inscribed angle subtended, remember, just means extended by the diameter. So let's start by drawing our diameter. We know that a diameter is a line that crosses right through the middle, and we'll put points on the end of our diameter. So if we extend anywhere to the outside of that circle, let's extend here to here, then those two lines we've created should make a right angle. Okay, so we could say that angle ACB is going to equal 90 degrees. So if we extend from either side of a chord where the chord is actually our diameter, then it's going to create that right angle. So the practice problems are going to get you to put these into play and make sure you understand what do these properties mean and how do we find inscribed angles, central angles, maybe certain lines of a triangle we formed based on some of those properties like the perpendicular bisector or lines of tangency. Okay, so give some of those practice problems a try, and that's it for your notes for today.